Okay, it's 10:40. Good morning, everyone, and let's start. Well, last time we talked about electric fields of multiple charges and how to compute electric fields of configurations of charges. Fundamental for that is the principle of superposition of electric fields, as we discussed. Well, the electric field at any point is given by the sum, the vector sum, of the electric fields created by individual sources and individual charges. And, well, if we're talking about microscopic bodies, if we're talking about charges that we deal with in our daily life, how many charges is that exactly? How many elementary charges? Well, it's a lot. In electrostatic experiments that you saw when, for example, a piece of amber is being rubbed against a silk sheet, or when a PVC pipe is being rubbed with a cloth, or just on all objects, plastic surfaces on my jumper, also known as sweater. Typical values of charges are microcoulombs. And, well, 1 microcoulomb, that's a lot of electrons. It's an equivalent of a lot of electrons. So that's approximately, I can write the exact figure, 6 multiplied by 10 to the 12 elementary charges. Well, an elementary charge is the charge equivalent to the absolute value of electron charge. So that's 6 trillion charges. And, well, it's a lot of charges, naturally, to compute the electric field of such an object. If we summed over individual charges, it could be a huge sum. And that applies to all objects, basically all plastic surfaces we see, to all pieces of clothes, trillions and billions of charges. And when we have that many charges, that many electrons, it's convenient to sometimes forget about the discreteness of charge. Well, charge is quantized. The charge that any object can have is discrete because any object can contain only an integer number of electrons, or like an integer number of electrons relative to its neutral state. But when we have trillions of those objects, it's convenient to just think about charge as something continuously distributed and introduce the density of charge. And that's exactly the subtitle I wrote here, charge density. And I'll explain it in somewhat more quantitative terms. So let's say this is our charged body that has got trillions of electrons in it. Well, so far as charge is concerned, trillions of excess electrons. The total number of electrons is even larger. And if we consider a small piece of that body, well, small in comparison with the microscopic length scales of that body, here I draw a cube of some very small volume delta V. Then we can just introduce the amount of charge delta Q in delta V, and if it's very small, to some good approximation, we can assume that the charge is distributed in that volume uniformly. And then we can introduce what's called the density of charge. So for a small volume, delta V, the charge delta Q equals rho, charge density, multiplied by the volume. And let me write here that that's exactly the charge density. Well, that's a qualitative explanation of what charge density is. Of course, a stricter mathematical definition would imply a limit. We would have to say that the charge density rho can be found as a limit of delta Q over delta V with vanishing delta V. And when we take this limit, we do have to forget about the quantization of charge, that is about the discreteness of charge, and think about it as a continuous quantity, which is indeed a good approximation. Well, indeed, electrostatic phenomena have been known for maybe 2,500 years since ancient Greece, but electrons were discovered slightly over 100 years ago. So, and all that time, for a couple of thousand years, people would think about charge as something continuous and would not notice its discreteness because the quantum of charge is so small compared to typical charges we deal with in devices and just in all objects that we handle every day. Does that make sense? And, this is analogous to a large extent to the mass density, which perhaps you discussed in the previous quarter in 5a. If we think about the flow of a liquid or a gas, that liquid or gas consists of discrete particles, atoms, molecules, but to describe them, one introduces a finite, continuously varying quantity called density. And just when the word density was mentioned in the past, so in those past contexts, in the context of mechanics, its meaning was how much mass you have per volume. And you would have a similar ratio here and a similar limit. Here, however, we are doing the same with charge. How many charge you've got per volume, and similarly we're forgetting about the discreteness of charge, thinking about it as a continuous quantity. Well, using charge density, we can find the total charge in an arbitrary charged body, so long as we know that the density is a function of location. So I'll briefly walk through that step. Also, we'll remind ourselves about the concept of integration. So to find the charge in the whole body, we can say that it consists of small elementary volumes, just multiple cubes like that. And we can label them 1, 2, 3, and so on. And just we can approximate the whole body by such small cubes. And and then we say that the total charge in the body Q equals the sum of charges delta Q1, delta Q2, and so on, delta Qn in those small cubes. and respectively we can express them through the density of charge. Delta Q1 is rho 1 of the charge density in cube 1, which could be assumed to be uniform inside that small cube, so long as it is small enough. That's a good approximation. Rho 1 delta V1 plus rho 2 delta V2 plus and so on, plus rho n delta Vn, where n is the total number of such elementary cells. And, well, that by definition could be rewritten as a sum over all such elementary cells, elementary cubes, rho I delta Vi. And whenever we have a sum over many elementary cells of some function with the values of that function, ideally, to approximate the quantity of interest very accurately, we have to consider the limits of the vanishing volume of those cells and an infinite number of those cells. Because, well, the smaller they are, the better we approximate the total charge there. And that limit, the limit of an infinite number of cells and the vanishing volume of each elementary cell, that by definition is called an integral. Rho dV. Well, in general in physics, whenever you approximate a quantity by a sum of small elementary parts and then send the size of that small elementary parts to 0, that's called an integral. And in the previous class in Physics 5a and in the prerequisite mathematics courses, you dealt with integrals, of course, but I presume those were one-dimensional integrals, right? So you would integrate a function of one variable. So you would introduce a variable x, divide the interval over which you integrate into small slices, and sum that function over those slices. This is the same, but it's done over a three-dimensional space. And so far, I'm only defining this integral. I'm not telling you how to take it. You know how to take one-dimensional integrals. Three-dimensional integrals like this, they are taken in a similar fashion. So the charge density, rho of x, y, z, depends on the location, meaning it depends on three coordinates, x, y, and z. And the volume itself, the elements of the volume dx, dy, dz. So it's quite similar to the one-dimensional integral you dealt with before, but to find this quantity, you have to integrate over three coordinates. You can do it one by one, say, take the integral with respect to x first, with respect to y, then with respect to z, and that's how you would find such an integral. But so far, I'm just defining that integral and introducing the concept of such integrals in 3 dimensions. I'm not explaining how to actually take it in practice. We'll get to that later. But so far, I hope it's understandable at the conceptual level. Okay, if there are no questions about this, then we can say a couple of words about the electric field of a charged body. And it's found in a similar way. So, again, I will not be taking integrals immediately. We'll come to that later. But I want to just introduce conceptually how we would find it. And, well, again, we would consider a very small volume, delta V. Well, of course, we could do a sum of a trillion, literally a trillion of electrons. That doesn't sound like a nice exercise. So when was the last time we did a trillion of something? So it's a huge sum. But if we say that the charge is, to some approximation, varying smoothly inside the charged body, then we can approximate it by a continuously varying function, charge density, and just decompose our body into small pieces and take a sum over them, and again take an integral, just in principle. So we can say that, let's consider a small elementary charge. Well, a small cell of volume delta V, not literally an electron, but it's small enough to approximate the charge density by something uniform inside it, on the one hand, but it's large enough so that it contains lots of electrons, and we can forget about the discreteness of charge. And at this point, at the point of interest, it will create some electric field which will be parallel to the unit vector r hat drawn from this element to this point, and the field E itself will be parallel to this vector r hat. Let me actually call it delta E, because it's a small field corresponding to a small piece of the body. So delta E equals K. The charge delta Q divided by r squared, where r is the distance from this element to the point of interest, r hat the direction. So the hopefully already familiar Coulomb's law, written in the vector form. So the first part is the magnitude, the second part is the unit vector, which shows its direction. So that equals K, let me write K r hat over r squared. Then delta Q I'll rewrite as rho delta V. Yeah, and that's it. So that's the electric field of this piece. Does it make sense? And the total field, the total electric field, according to the principle of superposition, is the sum of electric fields of all such elementary cells, of all small pieces. So it's the sum over all small pieces. Let's assume that we have labeled them, that is, assigned numbers to them, and then we go K Ri. Well, the unit vector is going to be individual for each individual piece, because their locations differ. So the directions of Ri hat are going to differ. The distance Ri squared from the ith piece to the point of interest, rho I the densities are also going to vary slightly from piece to piece. Delta Vi. And it's a sum that approximates the total electric field of a charged body. And of course, for that approximation to be more and more accurate, we have to divide that body into smaller and smaller pieces with sizes going to 0 and the number of pieces going to infinity. And we know what this limit is called. That's, again, an integral. So basically, I rewrite the same function. I say k r hat r squared rho, where rho depends on the location, dv. Well, that's an integral, and so far you can consider that as just the definition of an integral. So an infinite sum that approximates a finite size body. So far I'm not explaining how to take it in any practical setting. But already from here, it's clear that it's not going to be an easy task, because the function rho can be arbitrarily complicated. Well, from your experience with integration, well, perhaps you know that in general integration is a very difficult mathematical task, because if I give you an arbitrary function of one variable and you've got to integrate it with respect to one variable, you cannot do it for an arbitrary function, only for some given set of standard functions that are sufficiently simple. And the task of computing these sums of this kind of integrals, it's even more complicated, because you've got to integrate the three-dimensional space, meaning you've got to integrate 3 times over x, y, and z. It's going to be even more complicated. Or if you wish to find the total charge or the total electric field by summing over individual electrons, and it's a sum with literally trillions of contributions. Well, that motivates us to introduce Gauss' law. And Gauss' law is a law that significantly simplifies the calculations of electric fields and charges, as you will see. So I'll write down as a teaser what this is, but we'll need the whole lecture to introduce Gauss' law. So Gauss' law relates electric charges and the electric fields of those charges in an elegant way. Well, sounds promising. It does not mean that I'll give you a way to find the electric fields of an arbitrary distribution of charges. Well, rather it will be useful for certain standard symmetric configurations of charges. For example, when you've got a uniformly charged sphere, or you've got charge distributed on the surface of a sphere, or if you have a uniformly charged string there are lots of situations in which Gauss' law will very quickly give you the result for the electric fields in the whole space without doing summation over a huge number of contributions or without doing integration. And it's a really powerful tool. And well, as I said, probably I'm going to be introducing Gauss' law for the rest of the lecture. Unfortunately, perhaps from the mathematical point of view, from the conceptual point of view, this is the most difficult part of Physics 5C. And it's a little bit unfortunate that it comes that early in the quarter. But, well, the good news, if we get through that part, then it will only get easy from there. It will give some good training. And as you will see, it's a really powerful tool. Okay, that was just a teaser for Gauss' law. Just I haven't introduced it in any qualitative, let alone quantitative way. But in order to introduce it, I need first a few concepts. So the first one is going to be electric flux. And perhaps you've heard the word flux before. Maybe you've heard it in the context of dynamics of fluids, when you have a liquid flowing in space, you would introduce a surface and how much liquid passes through that surface per time. That would be the flux of that liquid. Well, if you haven't heard of it, but it's no problem at all. Just I'll introduce everything in due order. So what's an electric flux? So just as I just mentioned, flux in general, the concept of flux in physics, describes of how much something goes through an area, and it's the same for electric fields. So here's the strict mathematical definition. Let's consider a uniform electric field, E. Well, here I draw the lines of that electric field for a uniform field, meaning the field having the same magnitude and direction everywhere. It's just those uniform lines. So let me write uniform electric field. Let's consider a surface which is perpendicular to this electric field. Then the flux, denoted by letter phi, Greek letter phi, equals the electric field E multiplied by the surface area S. So that's the definition of the flux. So flux through area S. Well, I put it in a blue frame. What do I mean by that? It's an question.
What's S?
The area. Phi. The flux. That's the flux itself. And phi is the common notation for it. In principle, if you wish, you can use other notations so long as you explain them.
So is flux a scalar quantity?
Yes. Yeah. So here E, when I wrote E, I use the common notation for E, which is the magnitude of E, and S also scalar, and therefore it's a product of two scalars. But so far that's the definition of flux for just this situation when we have a uniform electric field and a surface perpendicular to it. It's not the most generic situation, because in general we can imagine an arbitrarily complicated field which is inhomogeneous in space and an arbitrary surface. And so far I haven't defined flux for an arbitrary surface for that situation. So far it's that simplistic situation, just flat surface perpendicular to the field, and that's how flux is defined in this case. But now we'll start generalizing it step by step, and we'll come to the definition of flux of an arbitrary non-uniform field for an arbitrary non-flat surface. Well, let's first make the first step. So I'll write here generalization. Surface not perpendicular to the electric field. And well, what it means is the surface is tilted with respect to the field. So that's the field. And now that's the surface. Now that's some angle here. And let's introduce what's called the orientation of a surface. So let's introduce a vector S, which we are going to call the area vector. That vector will be perpendicular to the surface, and the length of this vector is given by the area. That's why it's the area vector. And well, that does not uniquely define this vector, because although it's perpendicular, it could point in one of two directions. It can point this way, upwards. It can point downwards, and well, we'll choose one of those directions. We can choose it pretty arbitrarily, and if we make this choice, then we're going to call that surface orientated, aka oriented. And we'll say that we specify the orientation of a surface, and so the side to which that vector points, that's what we're going to call the outer side of the surface. And the other side will be the inner side of the surface. So we had a flat surface. It's got two sides, and we arbitrarily labeled one of them to be the inner side, the other one outer side. Well, that will make more sense when we consider closed surfaces. So far, those are just mathematical definitions, whose purpose may not be entirely clear. It may be a bit abstract, but we will see the usefulness of all of that later. And the area vector is the vector perpendicular to a flat surface with the magnitude given by the area. And then, in that case, when we have such orientated surface, the flux is given by E, the electric field, dot product S. So the dot product, also known as scalar product of two vectors. And again, phi is a scalar because the product of two vectors is a scalar. And just as a reminder, the product, the dot product of two vectors, well, I'll use these notations E and S. That, by definition, is the product of their lengths and the cosine of the angle between them. Does that make sense? Are there any questions about it? Well, so far it's just a question. Yeah, yes. So, yeah. So, indeed, when they become perpendicular to each other, then the bottom formula becomes the top formula. And so the top case of the perpendicular surface, that's a special case of this situation. But we introduce this definition for an arbitrary orientation of the surface and the fields just in order to define the flux in the arbitrary most generic case. Yeah, but of course, this limiting case is reproduced by this definition. Okay, does that answer your question? Yeah. All right. Does it make sense?
Yes.
Great. All right. I don't see further questions. Well, maybe let's consider an example. So let's consider a disk. So that's a disk of a given radius r, and there's an electric field E directed at an angle of 45 degrees to this disk. So the field is directed like this. So let's find the flux of that field through that disk. Well, of course, to find the flux, we've got to introduce an area vector, and the area vector has got to be perpendicular to the disk. So that's going to be the area vector directed vertically up. Well, we could have introduced it in one of two ways, either vertically up or vertically down. So let's choose up, and when we say find the flux of the field through a flat surface, we talk about already an orientated surface. So with a specified direction of the area vector. Otherwise, there are two ways to specify it. So let's say we've chosen S to be directed upwards. Then, by definition, the length of this vector is pi r squared. And, well, the flux equals S dot E, and well, the area vector is like this. It also makes an angle of 45 degrees with the electric field E, and it means that to find this vector product, we consider the length of S, the magnitude of E, which is also conventionally denoted by just E without the vector, and cosine of 45 degrees. And we plug in the numbers, I mean not the numbers but expressions for each quantity. So S is pi r squared, field is E, cosine 45 degrees is 1 over the square root of 2. And yeah, basically that's our result for the flux. Good question.
For the angle used for the cosine, are we finding the angle, just to clarify, between the field and the surface vector, or so the field in the normal vector, or the field in the surface?
Yeah, so we want to compute this dot product. Therefore, we need the angle between the field and the area vector. Okay, so the area vector, which is perpendicular to the surface, and the field.
Thank you so much.
And the dot product is commutative, right? So you can switch around with it?
Yes. Yeah, that's true.
Does this surface area vector equation always for a disk only, pi r squared?
Only for a disk. If it was a square, for example, with side A, it would be A squared. So if it was a rectangle, just with sides A and B, it would be AB. So it's specific to the surface. All right.
Would that be considered a final solution if this were just been like a quiz or a test? Like if we had values for the radius and electric field quantization?
Yeah, so if the values of R and E are given, then you plug them in. If they are not given, then you just leave the answer in this form. Well, in fact, in the next discussion section for the next week, there will be a problem of that type, and there will be a chance to practice. All right. And well, of course, the homework will be released soon. But yeah, whenever the numbers are given, you plug them in. All right. If there are no more questions about that, let's keep generalizing. So let's introduce the concept of a closed surface. So, well, a closed surface, it's a surface that encloses completely a piece of a region of space. So it divides the whole three-dimensional space into the inner part and the outer part. So let me write down the definition. Closed surface, that's a surface that contains a region of space enclosed from all directions. Enclosed from all directions. And one can give several examples. For example, a cube, the surface of a cube. That's a closed surface because, well, it divides all the space into the interior of the cube and the exterior, and just each side on the outside of the cube will have an outer side, and everything that's inside, so all the surfaces that are facing the inside, that's going to be called the inner side. And, well, another common example is a sphere. Again, it divides, well, I've drawn here the equator, but again, the sphere divides the whole space into the inside and the outside. So it's a closed surface. Well, another example, just I can draw something like a closed bottle. So I'll draw several equators like this, and that's the example of a closed surface. And so what would be not an example of a closed surface? So this sheet of paper, that's not a closed surface because it doesn't enclose any space completely. Even if I make a cylinder out of it, it's not a closed surface because it does not completely divide space into inside and outside. It's not closed on the sides. Right? Does that make sense? The concept of a closed surface. A question?
Just to clarify, is this in 3 dimensions only, or does this apply to different?
Yeah. We are talking only about 3 dimensions. And maybe now that I've introduced a closed surface, such surfaces could be of an arbitrary shape. Now we will be computing electric fluxes through surfaces of such arbitrary shapes, but to compute them, let me generalize them. I'll write here, generalization. Flux through an arbitrary curved surface. So let me draw an arbitrary curved surface. It's not necessarily closed. So this is something very distorted, very curved. And it's placed in an arbitrary electric field which is not necessarily uniform. We are going to compute the flux through it. And we have not defined it, so we defined only how to compute fluxes through flat surfaces. But the generalization to the case of a curved surface is straightforward. What we need to do is just to approximate this arbitrarily curved surface by pieces of flat surfaces. So what we are going to do, we are going to select a small piece here. And a small piece can be assigned an area vector. Well, it's quite clear that any realistic surface has the characteristic length scale on which it curves, if it is curved. And if we consider a small piece of that surface, which is significantly smaller than the curvature radius than the characteristic length on which it curves, then to a good approximation, that small piece can be considered to be a small piece. So let's consider a small piece of that surface. We're going to approximate it by a flat piece and respectively introduce a vector delta S1. And if it's a closed surface, then we'll choose the orientation of delta S1 to be directed just into the exterior, towards the outer side of the closed surface. So, and we can compute the flux through that flat surface. Then we can approximate the whole curved surface by a combination of flat pieces. So a piece like this, a piece like this, and so on. And we are going to label them. So this will be delta S2. This will be delta S3. And the flux through piece I, that's delta phi I equal to the electric field at the location of that piece. The electric field near that piece can also be approximated by the electric field can also be approximated by a uniform field, so long as the piece is small enough, multiplied by delta Si, the area vector. So the area vector is locally perpendicular to the surface. Then the total flux, phi, equals the sum over all small pieces, EI, multiplied by delta Si, so the vector of the dot product of two vectors. And then how do we define the flux for the entire surface? The flux for the entire surface is given by the limits of the sum of small flat pieces in the limits where the number of pieces goes to infinity and the size of each individual piece to 0. So the notation for it is going to be E ds, and that's called the surface integral And again, so far I'm just defining the surface integral as a limit. Just I'm not explaining how to compute it. But let me again repeat the definition. We have an arbitrarily complicated surface. It's arbitrarily curved. It may be very sophisticated, and arbitrary inhomogeneous electric field, which can also have some arbitrarily sophisticated dependency on space. So what we do, we approximate that surface by small local pieces, flat pieces, and sum the fluxes of those pieces, and then consider the limit of the number of pieces going to infinity and the size of each individual piece going to 0. And that's our surface integral. And that surface integral allows us to find, to relate the electric field created by a configuration of charges, and those charges themselves in a very simple way. So I'll write here Gauss' law, and that's the Gauss law itself. Finally, we come to it. So let's consider an arbitrary surface with some charges inside. So that's a closed surface. Those are the charges inside. And the sum of those charges is Q. They create some field around them. There can also be charges outside, which also creates an electric field. And the statement of Gauss' law is that the total flux, the total electric flux for that surface, I'll write it as E ds equals the sum of all charges inside divided by the constant epsilon naught. And that's Gauss' law. I'll put it in a red frame. It may look intimidating, but in the remaining couple of minutes and in the other lectures, we will be practicing a lot with it, and I'll be explaining the meaning of Gauss' law, and we'll be using lots of examples for it. So, first of all, what's epsilon naught? We may have already forgotten. So, epsilon naught is the constant that you have in Coulomb's law. I'll write here a small reminder. So, Coulomb's law is the force of interaction between two charges, just the absolute value of it. The product of the magnitudes of those charges divided by distance squared. And this constant k can also be written as 1 over 4 pi epsilon naught. So epsilon naught from here is 1 over 4 pi k. And so it has a name, this constant, that's the permittivity of free space. permittivity of free space. And well, another way to rewrite Gauss' law is to say that the flux through a closed surface, and it's essential that it's closed. Then we can separate all the charges into the charges that are inside of that surface and the charges that are outside of it. So the total flux through the surface is given by Q divided by this constant epsilon naught. And that's Gauss' law. Well, as I said, I think mathematically that's the most difficult part of the entire course. So definitely we are going to start next lecture with revising what I just said, just writing down Gauss' law and trying to use it. We still have 3 minutes. But I just want to finish. Just want to mention that. So definitely we will we'll discuss its physical meaning. We will do some exercises, and already in the next discussion section you will have a couple of exercises. I strongly recommend that at home you read the respective chapters in the OpenStax book or in Jan Coley. So you would need to start reading from the definition of electric flux and flux through surfaces. As you've seen, there are 3 stages how we define it. First for a flat surface, and for a flat tilted surface, and then as an integral. Yeah, are there any questions about this?
No. It's a little bit difficult to hear, unfortunately.
Oh, so whenever it's difficult to hear, just do complain, because I can adjust the volume. Yeah, in principle, we still have 2 minutes, but yeah, I see you're eager to stay here and listen a little bit more. But all right, so perhaps it's indeed a good point to stop, and I hope you have a wonderful weekend. And I'll see you on Monday. And today, as usual, there's an office hour. Yeah, thank you.
I was wondering, what is the permittivity of space? Is this...
So it does not refer to any particular region of space, so far as we consider indeed free space. So it's implied here that we consider free space. It's not filled by the medium or anything. So just the fundamental constants. And just whenever you are given a problem, you will be given the value of that constant. Well, it's always the same, but so that you don't have to remember it, it will be just always given to you.
Okay, and then also, when we're taking the dot product of E and S, if this is perpendicular to the electric field, wouldn't it be 0? Because cosine 90?
Oh, no, cosine of 90 degrees is 1. Well, sorry, it's a cosine of 0.